Welcome to day 31 of Math 111. In the lesson today, we're going to be considering decimal numbers and also real numbers. First, we're going to begin with a definition. Let's read this together. A decimal is a base 10 positional numeral, either positive or negative, in which there are finitely many digits to the left of a point called a decimal point that represents units, tens, hundreds, and so on, and a finite or infinite sequence of digits extending to the right of the decimal point that represent tenths, hundredths, thousandths, and so on. All of us have seen decimals before. We know what they are, but actually defining what this is very interesting to us. Let's look at this example. We've got 24 and 587 thousandths. What does this actually mean? We do have a positional numbering system, and so each position means something special to us. The 2 in our number represents 2 times 10. The 4 is in the units position. That's 4 times 1. The 5 is to the right of the decimal. This represents 5 tenths, or 5 times 1/10. The 8 is in the hundredths position. That is 8 times 1/100th. And the 7 is in the thousandths position. That represents 7 times 1/1000th. We can use base 10 blocks to model decimal numbers. What we have to do is define the unit when we do this. Remember how the pieces are related in the base 10 kit. 1 cube is equal to 10 flats. 1 flat is equal to 10 rods. And 1 rod is equal to 10 units. We're going to be using the word unit in different ways here. In the base 10 kit, you know what the unit is, but also whenever we talk about building a number with the base 10 blocks, we'll have to determine which of our blocks is our unit in our number. In this example, if the cube is defined to be the unit, or representing 1, then a flat represents 1/10. The rod represents 1/100th. And the little unit cube in the kit represents 1/1000th. Here we have a picture. What number does this model represent if a flat is our unit? So the flat represents 1. Think about this for just a moment. If the flat represents 1, then the cube represents 10. The rod would represent 1/10, and the little unit cube from the kit would represent 1/100th. What number did you get? I hope you got 12.18. That's 12 and 18 hundredths. Here we have another picture. What number does this model represent if the cube is our unit? Did you determine an answer? I hope you got 1.138. That's 1 and 138 thousandths. The addition and subtraction operations with decimals can be modeled with base 10 blocks, just like we did with the integers. The trading is done in the same way, both trading up and trading down. In modeling addition, both addends are built. With subtraction, only the minuend is built. I'd like for you to try some of these on your own. Let's talk about some characteristics of decimal numbers. Sometimes we talk about a terminating decimal. A terminating decimal is a decimal number which has a finite number of digits. An example here is 23.47. This is terminating because the decimal number has only 4 digits. There are 2 digits to the left of the decimal point and 2 digits to the right of the decimal point. Every terminating decimal may be represented as a rational number. What we're saying here is that every decimal number can be converted to a fraction. In our example here, we can add the fractions. Remember, we have a positional number system, and so each digit represents a certain quantity. So we have 20 plus 3 plus 4/10 plus 7 1/100ths. Remember that we add rational numbers by getting a common denominator. Our common denominator here is 100. We convert all of our integers and fractions so that they all have a common denominator of 100. And then we add the numerators. You can see that our result here is 2,347 hundredths. Practice doing this. This is a necessary skill. Which rational numbers have terminating decimals? You have noticed in the past on your calculator that some decimals come out with just a few digits, and then some fill up your whole display. Which ones actually stop? The only rational numbers which have terminating decimals are those that have denominators which are divisible by 2 or by 5 only. If the denominator is divisible by any prime number other than 2 or 5, then the decimal will not terminate. Your book includes a theorem for this. And the theorem states basically what we have already said. Let's look at an example. Let's take the fraction 3/20. When we convert this to a decimal, we are dividing. 3 is divided by 20. And you can do this on your calculator. You'll notice that you get the equivalent 0.15 or 15 hundredths. The only prime divisors of 20 are 2 and 5. We have another example here, 7/15. The prime divisors of 15 are 3 and 5. We know because of this that the decimal will not terminate. When you divide this on your calculator, you'll notice that you get 0.46, and then the 6 continues to repeat. You'll also notice on your calculator that the last digit on the right is a 7, and that's because your calculator will round up. So the decimal equivalent of 7/15 is not a terminating decimal. Here we have a definition. A non-terminating decimal with the property that a digit or string of adjacent digits repeats ad infinitum from some point on is called a periodic or repeating decimal. The number of digits in the repeating group is called the length of the period. Here we have some examples of some repeating decimals. I'm sure you're familiar with the first one, 0.333, and 3 would continue to repeat. Here, you only have 1 digit repeating, so the length of the period is 1. In the next example, we have 1.242424. The 2 and 4 are repeating. The length of the period is 2. And in the last example, you notice that it takes several digits before the repeating begins. You have 4.2355555, and so on. The 5 repeats. The length of the period is 1. These are examples of periodic or repeating decimals. In order for us to have a repeating decimal, then a divisor of the denominator must be a prime factor other than 2 or 5. We use a bar to denote a repeating element. These are the same examples that we saw on the previous screen. Instead of writing 0.333 ... we use the notation 0.3 with a bar over the 3. In the next example, notice that the bar is over 24, 1.24 with the bar, indicating that 24 repeats. And in the last example, notice that the bar is over the 5. The 5 repeats. The bar is used as soon after the decimal as possible. One way of converting a rational number to an equivalent decimal number is to use long division. Here, I'm showing you how we would find the decimal equivalent to 3/8. You've all done this in the past. This is something you should practice. We do have calculators that do this. Being able to do it by hand is valuable to you as a teacher. The prime divisor of 8 is 2. You'll notice I said the prime divisor. There's only one prime divisor of 8. 8 is 2 to the 3rd power. And because 2 is the only prime divisor, then this does terminate. So the decimal equivalent of 3/8 is 378 thousandths, or 0.375. Here we have another example. We're using long division to determine the decimal equivalent of 50 elevenths. We divide 11 into 50. 11 is a prime number. And because it's not 2 or 5, then we know this one will repeat. So notice the division taking place here. And notice the repeating pattern that is beginning. The repeat begins when we get a remainder that is identical to something we've had before. So notice that we started with a 50, and then we have a result down here about midway down of 50. When this happens, we know that we're beginning to repeat, and so we will look for that repeating pattern from there on. Notice how we express this with the bar notation. In the long division, we had a quotient of 4.545, and the 4 and 5 will continue to alternate. We use the bar as soon after the decimal as possible. So we express this as 4.54 with the bar over the 5/4. Here's a caution when using a calculator. Calculators frequently round the last digit. I mentioned this earlier. Repeating patterns may not be clear due to rounding. Sometimes also the repeating group is very long, and with calculators with limited display, you may not see the full repeating period, so be careful. How do we go the other way around? How do we convert a repeating decimal into a rational number? Well, the first thing you want to do is identify the repeating pattern. And then we usually multiply by 1 or more powers of 10. Here's an example. We want to convert this decimal, 0.365 with the 65 repeating, into a simplified fraction. Notice what we do here. We're going to let x be the original decimal given to us. What I want to do is multiply so that the decimal is to the left of the repeating pattern and also just to the right of the repeating pattern. This is why I multiply by powers of 10. If I multiply my decimal number by 1,000, this is going to move the decimal 3 places to the right. So I'll be going from 0.365, which repeats, to 365.65, and that 65 will continue to repeat. If I multiply my decimal by 10, the result is moving the decimal 1 place to the right. So this gives me 3.65 with the 65 repeating. So you'll notice here in the 2 multiplications I've done, I've moved the decimal place to the left of the repeating pattern in one and to the right of the repeating pattern in another. Just to emphasize, I've moved the decimal to the right of the repeating pattern here and to the left of the repeating pattern here. After I've done this, I want to subtract. The purpose of multiplying this way is to get the repeating pattern beside the decimal, and when we subtract, everything to the right of the decimal will subtract to 0. Notice what happens here when we subtract. 1000x minus 10x is 990x. When I subtract the decimals on the right, I get an integer now, 362. And then using algebra, I divide both sides by 990, which results in 362 divided by 990. And this fraction can be simplified. 2 is a common factor of both the numerator and denominator. And when I divide by 2, my result is 181 divided by 495. There are no other common factors, so this is my simplified form. This is a method for converting a repeating decimal to a rational number. We want to move now to the real numbers. The set of real numbers is made of 2 sets, the rational numbers and the irrational numbers. These sets are disjoint. We talked about disjoint sets when we talked about sets earlier in our course. To be disjoint means that there are no elements in common. So when we say that the rational numbers and irrational numbers are disjoint, that means that there are no real numbers that are both rational and irrational. So, what is an irrational number? An irrational number is a number which is not rational. Remember, a rational number is one which can be expressed as a fraction. So an irrational number is a real number which cannot be expressed as a fraction. The decimal expansion for an irrational number is non-repeating and non-terminating, which means it does not stop. You'll also not find a repeating pattern. Some common irrational numbers are pi, square root of 2, and square root of 5. All of your irreducible square roots are irrational. Now, moving to the ordering of decimal numbers. We talked about ordering of rational numbers in our previous lesson. The idea is the same here with decimal numbers. Ordering means to be able to express one decimal in relation to another using less than or greater than. Here's an example. Place the following decimal numbers in order from least to greatest. We have 2/10, 27 hundredths, 2 hundredths, and 3/10. I think knowing the proper names of the decimals helps in ordering. One way to help students understand the relative sizes is to use the base 10 blocks. With the base 10 blocks, you can define your unit and then build these types of decimals. It's pretty easy to see once the models are built which ones are small and which ones are larger. Another way to understand this is to rewrite all of the decimal numbers so that they have the same number of decimal places. You'll notice in our list that 2 of the numbers have 1 decimal place and 2 have 2 decimal places. If I rewrite all of these so that they have 2 decimal places, then they would look like 0.20, 0.27, 0.02, and 0.30. When we do that, we're thinking of them all in terms of hundredths. And so then it's easy to determine which one is the smallest, which one comes next, and so on, and which one is the largest. This is an activity that you will have to work with. Make sure that you can order decimal numbers. All of the properties that we have discussed in the lesson today are important. Make sure that you understand all this information about decimals and also the real numbers.